Okay, we have two more folks from Cray, Steve Woods and Dave McMillen. Steve Woods has worked in the HPC field for over 37 years, of which 12 of those years, his primary focus was the Lustre file system. His efforts with Lustre have varied over the years from development to support. Currently, he is Senior Storage Architect responsible for architecting large-scale storage solutions for Cray Incorporated. Dave McMillen is also Senior Storage Architect at Cray. He has gone back and forth between jobs as an end user and as a vendor. Most of his career, he has dealt with high-performance I/O problems. This is InfiniBand at a Distance. Steve? Sorry. Steve Woods. Let's hear it for him.
Oh, I love having the talk right before lunch, so I'll try to keep it short and sweet. Basically, long-distance InfiniBand, there's a lot of different use cases for it, but what we're going to primarily concentrate on is LNet and storage. I mean, you could actually do compute and expand it out, but when you start dealing with that with long-haul InfiniBand, there are a lot of non-trivial issues that you have to take into consideration. So what we'll concentrate on is what Cray primarily does with their systems, and I don't know if you're not familiar with Cray architecture, especially on the XC systems, the computes are all on our Aries proprietary interconnect, and how that accesses the outside is via what we are a series of I/O nodes, and those I/O nodes could be for login or local attached storage, or in this case for LNet routers. Some advantages of InfiniBand, long-haul InfiniBand. Well, you basically, in situations where you have a large complex where you may have storage at one end of a building and compute at another end of the building, and you need access to both, you may want to isolate it, and a good example is having the storage at one location and the compute at a different, but you still need access to it. We have situations where, especially in the weather forecasting arena, where they have duplication of systems. They have compute and storage at one location, compute and storage at the other location, but they need to cross-mount so that they have equal access between the two compute systems. Disaster resiliency. You may want your storage, for example, in a special place where it's not volatile to certain situations, and also to maintain some simplicity and interconnect. That might be an advantage also. Some examples. Here's an example that we primarily use, I've seen in the weather forecasting arena, where you have a compute system in, say, Hall A, and it'll have its own storage. You'll have another compute system in Hall B, and it has its own storage. But because of certain requirements, they need to see each other's storage. So if in the case of Hall B goes down, the weather forecasting can continue in Hall A. Should Hall A's storage go down, it can use the storage in Hall B to continue on. Or another situation is you may have compute in one location, you have compute and storage in the other, but they both need to share a common storage area. So here's a case where the one system is roughly less than 10 kilometers from where the actual storage and the other compute is. Here's an example I like, I thought was very interesting. We have a complex where there's compute in one building, compute in a completely another building that's roughly 10 kilometers apart, and they decided, well, we would like to have shared storage, and by the way, we have these bunkers. So they would like to put the storage in not just one, but two bunkers. So you have redundancy in the aspect that if something happens to like cooling or some issue or power in bunker A, you can still continue on bunker B. But both systems in building A and building B can have access to that storage, equal access to the storage. Now, let's see here. Yeah, okay. Now, there are other alternatives that we've seen in the past. You can have an all Ethernet infrastructure. You can actually go from IB to Ethernet through a series of LNet routers. or you could do Ethernet over WAN as another means of accomplishing something very similar. But of course, when you deal with Ethernet, you're pretty much stuck with the KSOC L&D, and we all know the somewhat lack of RDMA capability of that. You would most likely would not want to use the O2IB L&D. Now, how far is the distance? Well, believe it or not, you can actually see an impact in performance at 50 meters, cable at 50 meters. But luckily, what we've noticed in our dealings with the long-haul InfiniBand is that most of the applications, we are within a kilometer. Now, there are certain vendors that provide capabilities since extending it, because if you look at, for example, you can go to Mellanox, you can buy a 300-meter cable. But what about if you start to approach a kilometer or more? So there are devices out there like, for example, the Mellanox Metro X product. They have a switch that basically is set up to go a kilometer, 10 kilometers, 40 kilometers, and even up to 80 kilometers. And there are other systems out there too that you can do something very similar with, but they tend to get very expensive. Not that something like Mellanox Metro X can not be expensive too, but they can be quite expensive. Now, what's the problem with going distance? Well, since InfiniBand is a lossless network, it deals with its flow control across the links using credits. So in other words, when a transmitter runs out of the current credits, he stops transmitting until he receives a return from the remote side of a credit. So how many credits do you need? Well, using the equation time times bandwidth can kind of give you an idea of roughly how many credits you need to fill this particular pipe and keep things moving. And as I mentioned earlier, you can start seeing degradation with 50 meters. And it all depends on how many credits there are that particular link has by default. Basically, the bottom line is more credits mean more data in flight. With this calculation, I mean, this shows you some basic calculations of what the rate is for, QDR, FDR, and EDR. But basically, an optical cable takes about 5 to 5.5 nanoseconds per meter. So as you extend the cable, you can quickly see that the latency or interconnect delay kind of goes up proportional to the length of the cable. One thing is not in this calculation is the fact that there's actually a delay also associated with the transceivers for serialization and deserialization. And it differs from different models. Now this is basically to give you kind of a rough idea. If you have a short cable, you can keep the path full of packets. But here's an example of the 50-meter cable, whereas you can start to see gaps. And so what basically results in you may not get your full bandwidth because of these gaps and not being able to keep the pipe full because you don't have enough credits. The optimal goal is the bottom line where you have everything, enough credits to keep all the packets full. Now, if you can't, how do you get more credits? Well, one way is to steal them. Each virtual lane has a series of credits. So if you cut out some virtual lanes, it's kind of a cheap way of getting a little more credits to keep on going. If you can't do that, well, then you have to start looking at some type of specialized switch, as I mentioned earlier. The ones we've tested is the Metro X. But what you'll notice that each series where you go from 1 kilometer to 10 kilometer to 40 kilometer version to 80 kilometer, if you look at the port count, you go from 16 local and 16 long haul to 6 local, 6 long haul, to 2 local, 2 long haul, to 1 local, 1 long haul. So the number of active ports on each one of these switches actually goes down because that's how they end up, they kind of steal credits in order to maintain keep the pipe full. So basically, if you have a short cable, you have enough credits, you can keep the pipe full, you can keep the bandwidth on it. For as you go for longer distances, it gets a little more complicated. And Not to mention the fact that you physically have complication because coordinating efforts between one location and the other location. And then also there are other things to consider when you start doing long haul is where is everything being run? Am I susceptible to any type of power fail? When I run my cables, if I'm running long haul, I don't want to run all my cables to the same path. So if you're a kilometer or 10 kilometers away from two different locations, what you probably want to do is have part of the links going one direction and part of it going a different direction, because inevitably somebody's going to be using a backhoe someplace and decide to cut through your cables, and you don't want to lose your access that way. And also you need to be taking into consideration where the InfiniBand subnet manager is. For example, if you have switches at one location and another set of switches at the other location, there's a kilometer or 10 kilometers apart, you probably want to run subnet managers at both locations and backup subnet managers. Therefore, if somebody comes along and cuts the cables in between a backhoe, both ends can continue to function. And my cohort in crime, Mr. Dave McMillen, will go over the test results.
Thank you. So I apologize. When we first proposed to do this, we thought we'd have some more hardware. The test setup is relatively simple. We've got a single OSS. It's a Synexion-based system where it's one OST per OSS normally. We put a single OSS behind a long-haul link. We have a short link, standard half-a-meter cable kind of local connection. We have a 100-meter local connection, but 100 meters. And then we have a 1 kilometer connection to show the effects. So I wanted to go through some of the different things. The first thing I wanted to look at was just the raw InfiniBand. So this, for those of you that work with InfiniBand, this is just IBSend BW, looking at what kind of bandwidth can we get at the different MTUs. The one thing that you'll notice right away is that the 1 kilometer is running FDR10 link as opposed to the FDR on the local links. So we immediately lose that performance difference going from FDR to FDR10. But other than that difference, you can see that it holds up pretty well for things, and there's not a huge amount of difference, but you can sort of see what's going on. And for those of you that run tests, you know that you always get contrary results like that third one, where the 100-meter cable is faster than the short cable. Welcome to the real world. Latency, which is important sooner or later, shows up, and obviously at that point you can see the difference in the cables. The larger the amount of data you're sending, the less that latency turns out to be an issue. But this gives you an idea of what's happening at the raw InfiniBand level. And then more to the point for Luster is LNet self-test, where you're trying to figure out what can we really do LNet-wise. And I'll be honest with you, I knew that we were going to be close, that we didn't see a lot of degradation. I was pretty surprised at this set of numbers being almost identical across the different cables. It's much denser packing than I expected, almost no impact of having the long distances. Obviously, so I don't know how many of you run LNet self-test. Concurrency is how many different packet exchanges you've got going simultaneously. And basically, in some sense, you could argue it's the number of nodes trying to talk to your server, if you will. Clearly with only one node, with only the concurrency of one, you just can't push that much stuff into the pipeline. But it's equally true for the short pipe as well as the long one. And there's not a huge difference. I mean, the ratio of performance at one, concurrency of one between the local half-meter cable and the kilometer cable is it's only about a 25% loss. So it's pretty useful. When you move out to 1 megabytes, which is what we typically will see for reads and writes, at that point, you've almost lost every possible differentiation between length other than the FDR10, FDR difference. I mean, you can see those numbers once we get to a concurrency of 16 on the writes and even just 8 on the reads, we're already essentially identical. And you know, again, I was a little surprised it was as tightly grouped as this, but pleasantly so. We do have this deployed, and unfortunately it's in sites where we're not able to take measurements and give you results. So all I knew was that they were relatively happy, but I think I figured out why. So this is IOR. So again, I told you the setup was a single OST on a single OSS. The metadata server was not behind the long line, so I didn't run any MD tests. You know, there was no point. But this lets you see what's exactly going on. This is a straight up IOR running up to 64 individual nodes. I ran 1 rank per client, 1 rank per node, but all the nodes are talking to the same OST. So this is, in fact, sharing the OST. And you can see some variation. Again, you can see some unexplained. Why is the 100-meter link faster than the half-meter link? Probably just hit an interesting part of the disks for that part of the test. But the bottom line is at this level, you're not actually seeing much difference in the distance. Here's 1 megabyte sequential reads. That's even a little tighter grouping between the different cables, obviously a little more tail off for the different sizes. And then for random I/O, I've been watching these talks from Dresden and DDN about their multi-million IOPS. And you know, this is 54,000 IOPS at best, random I/O. So they obviously have much nicer servers than I was using. But this is where I really expected the kilometer cable to cause problems. And again, I'm seeing absolutely no differences whatsoever, within pretty close tolerance. So that's random writes. Random reads are much, much slower. If you notice actually random writes are pretty slow. That's just a little over a gigabyte, and that's now dropped down to, the middle of that is 600. Those were 1 megabyte random IOs, which are obviously a lot easier to cope with. When you drop down to 4 kilobytes, the random writes are abysmal. I mean, those are, but they're equally abysmal whether it's a local cable or a remote cable. So that's pretty much entirely an artifact of the server itself rather than the physical distance that's out there. And then same thing for reads, although reads did considerably better on their performance. So what's the takeaway from this? As you saw from, we got down to concurrencies of 1 or single rank IORs, the performance is down. You have to worry about if your intention is to do single client operations, then distances are going to matter, and you got to find some way to fill up that pipeline. There's lots of ways to do this. Globus has got some pretty interesting clients that do exactly that. Obviously not with the Lustre protocol. Usually this is, it's easy for me to go in and say, just figure out how to, quintuple buffer and it'll start working better. But the real answer is that almost nobody can figure out how to change their code to accomplish that. So it's not easy to fix. But once you get multiple clients, and as you saw in many cases, 8, 16 is enough multiple clients. But certainly by the time you get to on the order of 100 clients, the amount of interleaving that's going on already, just by virtue of having all those clients, completely overcomes any issues raised by those cables. And up to about 10 kilometers, you really won't be able to tell that you've actually strung out your InfiniBand that much. It's pretty amazing. There's another lesson to be taken from this, by the way, which I frequently say, and then I frequently get misquoted, which is that switch hops don't really count with Lustre traffic in InfiniBand. But what does matter, the guy from Harvard mentioned it, is congestion. And every switch hop gives you the opportunity to introduce congestion. So you have to be very, very careful about how you design it, as he was suggesting. And similarly, if you do these long haul things, you're going to be creating sets of switch hops to create that long haul infrastructure. And so you have to worry about, are you going to create congestion points in your network? But if you can avoid the congestion points, you won't have any problems. So, I'm trying to tell you that if you have a need to do something like this, don't be particularly afraid of it. I mean, I'd be happy to talk to anybody that wants to talk about the experience. Like I said, we have several deployments in the field right now that are quite happy with what they're getting out of all this. We have some potential work coming up that's going to go beyond 10 kilometers, and it'll be interesting to see how that goes. Any questions?
I do.
Yes, sir.
Can you tell me anything about the workload? Because, I mean, I don't know, we've got Lustre.
About the real production workload?
Yeah, I mean, we've got Lustre mounted across, 80 kilometers using Ether, and you're right on about congestion. I mean, we've got laboratories in Indianapolis that are pushing data to Bloomington.
Right.
I mean, so we kind of know those workflows. I mean, can you tell me anything about, I mean, I know there are possibly issues.
So as I best understand it, and I don't have any actual knowledge because I don't have the certification, the classification levels, security clearance. But as best I understand it, it is reasonably large sets of jobs running that are accessing a fair number of files of data that's being held in multiple locations.
So they're doing compute in place?
Compute in place.
Nice.
So we have moved a lot of our work to compute in place. We're tying more and more of our file systems to multiple computes. These days, typically when Cray delivers a new computer with new storage, we're busy wiring up that same storage to the existing computers, and even wiring up the existing storage to the new computer. That's just becoming extremely commonplace. And I think it's a better use of resources.
I love compute in place.
Pardon?
I love compute in place. Have for 11 years, as you pointed out to me earlier.
So-
It rocks.
Well, it's not 11 years, it's 11 times that you've showed up here, but it's only 10 years to get to 11 times.
Well,
You can come twice in 1 year. In fact, you did.
I think I've only been to Portland. Oh, you're saying here. I mean,
You came to LUG less than a year ago at another location. But hey, I'm sorry, I'm a techie.
No, I'm a little congested now. Sorry.
Well, I'll tell you what, why don't you go get yourself more congested with some lunch?
That's a good idea. Are there any questions? Thank you.